Hello and welcome to Precalculus lesson number 23. In this lesson, we're going to learn about variation. The first type of variation we will study is called direct variation. Technically speaking, we say that y varies directly as x, or equivalently that y is directly proportional to x if y equals kx for some constant k belonging to the set of real numbers. In other words, for some real number k. To say y varies directly as x or to say y is directly proportional to x are basically saying the same thing. K we call the direct variation constant, or also the constant of direct proportionality. Sometimes we leave the direct out and we just call it the constant of proportionality. Same here, we can just say variation constant. We usually leave the direct out, but to be really complete, you can include it in there because there are different kinds of variation as we're going to learn. Note that the values of directly proportional quantities either rise together or fall together. That's the real essence of direct variation. Direct variation is a relationship between quantities that increase together and decrease together. As one goes down, so that goes up, so does the other, and as one goes down again, so does the other. Now suppose that you have y, which is directly proportional to x, and also suppose that these two ordered pairs, now remember, these could just be pairs of numbers, they satisfy the relationship y equals kx. This we call the direct variation equation. Now, since these two ordered pairs satisfy this equation, that means y1 equals k times x1 and y2 equals k times x2. Now, if we look at the ratio between y1 and y2, like so, we notice that we can replace y1 with kx1 and y2 with kx2. So we get y1 over y2 equals, notice here, the k's cancel out, equals x1 over x2. This here is called the direct variation proportion. Now, both the direct variation equation and the proportion are important, and they can help us solve problems involving direct variation. In one case, the direct variation equation, you are required to find the constant of variation first before you can solve for other quantities involved in the direct variation. With the direct variation proportion, you don't have to find the constant of variation first. So this is kind of like a shortcut that helps us bypass that. But a lot of problems require us to find the constant of variation anyway. So what we will do is, as we do these problems, we'll do them in both manners. We will do them where we have to find the constant, and we'll also do them where we don't. So we end up using this proportion, and we'll show that there are basically equivalent methods. They end up with the same result. All right, so to make better sense of all this, let's look at an actual example. Y equals 2x is almost a classic example for providing a direct variation scenario. So note that the variation constant here is 2, and also if you look at the table just for a few values, and notice we're just picking a few nice values, otherwise we could have picked any real number value for x. We could have picked 0.2, 1.5. In fact, we could have picked negative numbers, etc. But just for simplicity, notice if x is 0, y is going to be is going to be 2 times 0, which is 0. If x is 1, we get 2 times 1, which gives us 2. If x is 2, we get 4, etc. You can see it's almost like the doubling function. So we notice that as x values increase, so do y values. And they're doing so at a constant rate of basically 2. So notice that as y values increase, so do x values. So they go up together, they go down together. And if we pick any two ordered pairs, right? Like for example, if we pick 1, 2, and 3, 6, right? Notice that 1 is to 3, x1 is to x2, as y1 is to y2. Remember where you saw that? Right here, where we divided by 1 by y2, and we ended up with this. So, which says basically x1 over x2 equals y1 over y2. Doesn't matter which one, if you write this on the left, this on the right, or vice versa. So in other words, the ratio of any two x values is the same as the ratio of the corresponding y values. Now, you can try this with any two other two ordered pairs from the table as well, or any two other values that satisfy the relationship y equals 2x, and you'll see it's true. Go ahead and pause the video and try it. So here we're going to actually solve our first variation problem. We're given that y varies directly as x. We're also given some information that when x is 6, y is 8. We want to find x when y is 10. I usually like to gather all that information in a table because it makes it easier for me to access it. So I can see when y is 6, x is 6, y is 8, and we're trying to find x when y is 10. So this is the scenario. The question mark is what we're solving for. All right, so in the first case, we want to do this by finding the variation constant first. So to do so, first of all, we realize that the general variation equation here is just going to be y equals kx for some constant k. We don't have it yet, but we can find it. In fact, we could take the ordered pair, both of whose component we know, to find the value of k. So for y, I'm going to plug in 8, and for x, I'm going to plug in 6. So I get 8 equals k times 6. Now I just solve this for k. So I get k equals 8 over 6. Of course, 2 goes into 8 4 times, into 6 3 times. So we have k equals 4/3, right? So now, this was the general variation equation, or the form really. For this particular scenario, the specific variation equation that applies in this case is going to be y equals, instead of k, we're going to put 4/3 x. So this is the direct variation equation that shows the exact relationship between x and y. Basically, every y value is 4/3 the corresponding x value. Of course, we can solve this for x2. We would get x equals 3/4 y, right? So now we're trying to find x when y is 10. So here we plug in for y, so we get 10 equals, remember, we're substituting 10 because that's what we're given, and we're going to find out the corresponding x value, and we'll be done. So we get 10 equals 4/3 x, which I can write as 4x over 3, and I'm doing that for a reason, because I'm going to go ahead and throw a 1 down here too, and then I'm going to recognize a proportion here that I can cross multiply with. So I get 4x equals 30, so x equals 30 over 4. 2 goes into 30 15 times, it goes into 4 2 times, so we have x equals 15 over 2. And that's the x value when y is 10. Now, here, we're asked to find x without finding the variation constant first. So, we're going to use the direct variation proportion. Remember, the direct variation proportion said if you have two ordered pairs, x1 and y1, that satisfy the relationship, then x1 is to x2 as y1 is to y2. So now you can see right here, we can think of this as x1 what we're looking for is going to be x2, but in this case we're just going to write x for it because that's the only unknown here, equals y1, which is 8 over 10. So this is a very quick method, but it does not give you the constant of proportionality. But if you just want to get to a quick answer, this is by far the fastest method. So here we're going to get 8x equals 6 times 10. So x equals 6 times 10 divided by 8. Of course, I know 8 goes in, 2 goes into 8 4 times, goes into 6 3 times. Also, 2 goes into 4 2 times, and into 10 5 times. So we get x equals 15 over 2. Of course, we get the same answer. We expected that. But notice this is the method where you have to find k first, and then go find whichever value you're looking for. Here, all we do is we use this ratio and set up this proportion with these two ratios from the table. x1 is to x2 as y1 is to y2. So since they're all known, we just call, used x here for simplicity, so we don't have to keep using a subscript. And then we just solve for it, and we get this. So x equals 15 over 2 when y equals 10. Okay, they're very simple. It's an important concept, variation, but the notions are not very difficult. Okay, so here we have another example. We have u varying directly as the square of v, and we know that v is 2 when u equals 20, so we want to find u when v equals 3. So first we'll set up the general variation equation, so we know u varies directly not as v, but rather as the square of v. So we have u equals kv squared instead of just v, right? So we're also going to tabularize the information given to make it nice and organized. So we know that v is 2 when u is 20. So there's one line of the table. We want to find u when v equals 3. So here we're just going to leave that as u and we know that v equals 3. So the first thing we'll do is we'll use this line from the table where both values are given to find k. So for one efficient method is actually, since we're going to be looking for k, solve this equation for k, then substitute. So notice you get k equals u over v squared. Just divide both sides by v squared. So we have k equals u over v squared. So we're going to substitute values from the first row. So for u, we're going to put 20. For v, we're going to plug in 2, so we get 2 squared. And of course, that's 20 over 4, which is 5. So we just found the constant of proportionality, or the variation constant for this problem, and it is 5. So now we can write the specific variation equation for our situation here. So we get u equals 5 v squared. Now all we have to do is use this information to find u. So we're going to substitute 3 for v. So we can say when v equals 3, we get u equals 5 times 3 squared, right? So we get u equals 5 times 9, which is 45. So if you want to answer it real professionally, you would say u equals 45, then v equals 3. All right, so that's the classic approach with finding the constant first and then stating and using the direct variation equation. Now we can do this also without the need to find k. Remember, we're going to set up our proportion first. But to set up our proportion properly, we need to look not at the table, we need to look at the equation, right? So we're going to have u1 is to u2 as, if this were just v, we would have said v1 over v2, right? But it's v squared. So can you guess what we're going to write? You should pause the video and guess and then come back. Okay, so I think you guessed it, v1 squared over v2 squared. So now we can substitute values, so we get 20 over u. Here it's just u1 and u2, so we don't need to square or anything. So we get 20 over u equals v1 squared. So be careful, don't just put 2 over 3. You have to say 2 squared over 3 squared. Always like to show you more than one method, because when you can solve the same problem with more than one method, you start to gain some real depth into the concept and mathematics itself. All right, so we have 20 over u equals 4 over 9. You recognize this? Yes, you said it. It's a proportion. So we can cross multiply. So we get 4u equals 9 times 20. Now we divide both sides by 4. So of course the 4's cancel out here. So we get u equals, do you notice when I do the cross products, I don't multiply it out? Have you been paying attention to that? That's because if I just leave it as 9 times 20 rather than just work it out in my head and put 180, then I can much more easily see any possible cross canceling, as I can see now. See, so 4 goes into 4 once, into 25 times. All right, so we get u equals 45. Not surprisingly, because we'd already done it, and of course that's when v equals 3. All right, so we get the same answer, obviously. But in one scenario, you had to find the variation constant first, and then find the value of u. In this scenario, we just go directly for the value of u, bypassing the need to find the value of k. But there is a lot to be said for finding the value of k, because now we know the exact relationship between u and v, and now if we are given either one of the two, we can quickly find the other. So yeah, we do a little bit more work in the beginning, but it pays off in the long run, because now we can find either value very quickly now that we have this variation equation. As an example, for example, if I say to you, also find v when u is, say, 10, right? So now you're going to just use that equation. So you're going to put 10 equals 5 v squared. So you get 2 equals v squared. So now we're going to just take the square root of both sides. So we get v equals, of course, the technical point here is that there are two numbers whose square is 2, either positive or negative square root of 2, but let's assume that we're dealing with positive values here. This is just an example for us anyway. We can assume anything we want. So since we really haven't dealt with these, I'm sure you've seen radicals before, but since we haven't dealt with them a whole lot before, we'll leave more analysis of this kind of thing for later. But I just wanted you to see the power. Once you have this equation, you can solve for either one given the value of the other. So here's an application. It may not look like a variation problem, but you'll see in a minute that it actually is. We're talking about Maria, who gets paid at a fixed hourly rate. On a week that Maria worked 20 hours, her weekly pay was $198. How many hours does Maria need to work in a given week if she wants her weekly pay to be $594 so that she can buy a phone that she's interested in? All right, so here we're going to let P be the weekly pay, and we're going to let H be the number of hours of work in a week. So notice that our equation is going to be simple. It's going to be P equals some constant of variation times H, right? H is the number of hours worked. So you see what the K is going to be here? That's basically going to be the hourly rate. So let's set up a table for the information we're given. So we know that when Maria worked 20 hours, she had a pay of $198. So now we want to know how many hours does she need to work. So the H is the unknown if she wants to make that much money. So 594 goes here. So you can see that we have this information from which we can find K. So we have 198 equals 20, that's H, times K. So K is going to be 198 over 20. So we can get some help from our calculator. So we have 198 divided by 20, 9.9. So now we're going to set up our variation equation. So we get P equals 9.9h. And remember, we want to substitute 594 for P to find the number of h. So we get 594 equals 9.9h. So h equals 594 over 9.9. Let's bring back our calculator. So 594 divided by 9.9. 60. Now, remember, this is not a very realistic situation because, as you know, first of all, she can't be really getting paid that much because the minimum wage, I believe, now is $15. So this is, imagine that this is a problem from several years back, all right? And it was a time when, you know, if somebody, let's say, in the service industry wanted to do more than 40 hours, they probably could sign some kind of an agreement that do it. And that's also unrealistic, 60 hours. But the point is, you can set it up using the methods of direct variation. So if we don't get too much stuck in the details and the fact that the situation is unlikely, it's not impossible, of course. It's possible to work 60 hours in 1 week, but it's unlikely nowadays. So there we have it with finding the constant of variation first, and the variation constant, and then using the formula that we've come up with, the variation equation, to get the value that we're looking for. Now we can also do this without finding the constant of variation. So in other words, we can find how many hours she has to work without even knowing the hourly rate. So the way we'll do it, of course, remember, you get your variation proportion from the way the equation looks. So we get P1 over P2 equals H1 over H2. And now we're going to use values from the table. So 198 over 594 equals 20 over h. So if we cross multiply, we get 198h equals 20 times 594. And now we're just going to divide both sides by 198. These cancel out, of course. So we end up with, so we want to do 20 times 5. Let's bring it back. 594. That's 7. And we're going to divide that by 198. Now, the moment of truth, right? When we hit that, we better get 60. And we do. All right. So once again, we end up with h equals 60. So these methods obviously will always generate the same results, but it's really, really powerful to know both. The next type of variation we want to talk about is inverse variation. Now, in direct variation, quantities go up together and they go down together. The exact opposite holds for inverse variation. First of all, we say that y varies inversely as x, or equivalently that y is inversely proportional to x if y equals k not times x but over x. So for some real constant k, what this is going to do, this fact that instead of y equals k times x we have k over x, it's going to create this situation when x goes up, y actually goes down, and that when y goes up, x goes down, and of course vice versa. So let's see if we can get the inverse variation proportion quickly. So we know that y is inversely, typo, proportional to x, and suppose these two ordered pairs satisfy the inverse proportion or inverse variation equation, right? Inverse proportionality, I should say. Then y1 is going to be k over x1 and y2 is going to be k over x2. So if I divide y1 by y2, I basically get k over x1 over y2, which is k over x2. Remember, we have when we have one fraction over one fraction, we can do the outer product over the inner product trick. So we get y1 over y2 equals kx2 over kx1. Notice how the k's cancel out. So when we have inverse variation, instead of getting y1 over y2 equals x1 over x2 like we did in the case of direct variation, we get the reverse. We get y1 over y2 equals x2 over x1. Of course, you can play around with this, and you can also realize this. You can also say x1 over x2 equals y2 over y1. So in other words, as long as these positions are the reverse of these positions for the x's and the y's. So this is the inverse variation proportion that we can also use to solve these problems. Either this form or this form makes no difference. We usually actually go with that form. And you can see how to get it, right? Just if you want to verify if this is true, make sure that the cross products are the same as they are here. Notice the cross product, this one is y1 x1, see that? And this one is x2 y2, we have that too. So, and you can also cross multiply this and get x1 y1 equals x2 y2. Now if you want to get this form out of it, just divide by, all right, we're going to divide both sides by, first of all, x2, because we obviously want x2 there, and we also need to get rid of y1. So if we divide both sides by x2 y1, look what happens. The y1s here cancel out and the x2s here cancel out. So you get x1 over x2 equals y2 over y1. Okay, so this definitely comes from this fact. So, and vice versa. If you have this, you can prove this is true too. So the main thing to pay attention to are two key points. In inverse variation, as if two quantities are inversely proportional, as one goes up, the other goes down, and vice versa. As one goes down, the other goes up. Secondly, when you want to look at set up the variation which bypasses having to find the constant of variation k, you don't set it up as x1 over x2 equals y1 over y2. You have to set it up in the reverse form. So the ratio of x1 to x2 is like the ratio of y2 over y1. Here's a classic example when it comes to inverse variation, y equals 2 over x. If you look at the table, let x increase, like from 1 to 2 to 3 to 4. Look at the corresponding values of y. Look, if x is 1, you get 2 over 1, so it's 2. When x is 2, y is going to be 2 over 2, which is 1. When x is 3, y is going to be 2 over 3, right? When x is 4, y is going to be 2 over 4, which is 1/2. Notice x values are increasing. What's happening to the y values? The corresponding y values are decreasing. You can also look at it this way. What if x values decrease? Then the y values do what? They increase. Okay? So also, if you pick any two pairs of points, like I picked the first and the last one, 1, 2, 4.5, right? Notice that 1 over 4, 1:4, if it were direct variation, we would have said is as 2 is the 1/2, but this is inverse variation. So we're verifying to see if 1:4 as 1/2 is to 2. Just change the order of the ratio creation. Here we're going from left to right, 1:4. On the other side, you're going to go from right to left, so you're going to say is 1/2 to 2. And let's see if it's true. But look, 1/2 over 2, that's like 1/2 over 2 over 1. Then we can do the outer product, which gives us 1 times 1, and the inner product, which gives us 2 times 2, so we get 1/4. So yes, it's true. And this will work with any two pairs. Just make sure that you do the left-right and then the right-left. Try it with a couple of other pairs before you continue in the video. Alright, so here we have that y varies inversely as x. So we know what that means. That means y, let me go back to blue. That means y equals k over x for some constant, real constant k, right? We also know that when x is 6, y is 8. We'll go ahead and set up a table to help us organize that info. When x is 6, y is 8. Now we want to find x when y is 10. So we want to know if y is 10, what is x? So we can just leave it as x. Alright. So now we're going to use the line in the table which has all the values accounted for to find k. If you want, you can solve for k first, just cross multiply, so you get k equals xy, right? Now substitute 6 times 8, so you get k equals 6 times 8, so k equals 48. So now I can write the inverse variation equation, which is going to be y equals, instead of k, I can now put 48. Okay, so there is the inverse variation equation. So now that I know this relationship between x and y, I can easily find out what x is when y is 10. So I'm going to put 10 for y. I'm going to have 48 over x. And if I throw a 1 down there, I can just cross multiply. So I get 10x equals 48. So x is going to be 48 over 10, which is 2 goes into 48 24 times, and into 10 5 times. So x is 24 over 5 when y is 10. Notice you can also say 4.8. Either one is fine. Usually when you use systems like MyMathLab, they'll specify what kind of answer they want, so just pay attention to that. Now we want to find x without finding the variation constant, okay? So remember, this is going to be easy. You just have to set up the ratio properly. So we're going to say, remember, x1 is to x2 as y2 is to y1. Remember, this is inverse variation. So we're going to put 6 is to x as, now be careful, if this were s squared or something, then you would have squared accordingly, but it's not, right? So as y2, which is 10, over y1, which is 8. Cross multiply, so we get 10x equals 6 times 8. So x equals 6 times 8 over 10. Now we cross cancel, 2 into 10 5 times, to 6 3 times, so we get x equals, not surprisingly, 24 over 5, which is the same answer, of course. In one case we have to find k first and then plug in to get the other value. In the other we can go for it directly. Now here's one with a slight twist, because u varies inversely not as v but as the square of v. So we're going to set this up as u equals k over v squared. Let's set up our table of values based on what's given. We know that v is 2 when u is 5. We want to find u when v is 1. Okay? So you know the drill. Pause the video, go figure it out, then come back. Let's see if we agree. So here we have k that we're looking for, and we're going to use those two values. So this time let's just go ahead and plug in. I want you to mix things up. Last time I solved for k first, then I plugged in. I want you to know you can just plug in too. So 5 equals k over v squared, which is 2 squared. So we get 5 over 1 equals k over 4. Therefore k equals what? K times 1 is k, 5 times 4 is 20. So we get u equals, instead of k now we can put 20 because we know the value of k, over v squared. So now we want to know u when v is 1. So we have u equals 20 over 1 squared. So we get u equals 20. Of course, that's when v equals 1. Now we can also do this without having to find k first. So we're going to set up our variation, but you have to be careful because you're going to have u1 is to u2 not just as v2 is to v1, because we have squared here. So as v2 squared is to v1 squared, like so. So now we substitute. So we have 5 over u equals v2. Remember, this is v2. This is u1 v1. This is u2 v2. So v2 squared, which is 1 squared, over v1 squared, which is 2 squared. So we get 5 over u equals 1 over 4. Now we cross multiply. We get u equals 5 times 4, which is 20. And again, that's when v equals 1. So you can see this method is extremely efficient if you become good at setting up these proportions, but only use it when the problem doesn't demand the variation constant. when it does, you should go ahead and do it this way. So here's another application problem that is related to variation. Chris can travel a given distance in 2 hours if he travels at 60 miles per hour. How fast would Chris have to go to cover the same distance in 1 hour? Now we're letting D stand for distance, R for speed, and T for time. As you know, D equals RT, right? So if I solve that equation for R, I get D over T. So the fixed value here is the distance that doesn't change, right? So you can see that's going to be the constant of our proportionality. So we're saying speed is directly inversely proportional to time, right? When the distance is fixed. So this is playing the role of K. And let's put in the values into a table. We know that when the rate is 60, the time is 2. We want to know what rate so that the time is 1. So now we're going to go ahead and rewrite this as R equals K over T to make it a real variation equation, and we can substitute. So we have 60 equals K over 2. So if we cross multiply, we get K equals 120. So now we want to rewrite this equation as R equals 120 over T. So now we're going to go ahead and plug in T equals 1. So we get R equals 120 over 1. So we get 120 miles per hour. So, all right, so one question is, do you recommend that Chris try and cover the distance in 1 hour? I think not, right? We don't want Chris to get in trouble. So in order for this to happen, Chris would have to go 120 miles per hour, which is not recommended except on a racetrack. All right, so when Chris asks you to figure this out, in the end of it, you say, Chris, I have a number for you, but you're not going to do it, okay? So what does the variation constant represent? Remember, that represents that fixed distance that was in question here. All right, so of course, at 60 miles per hour, which is reasonable, he could do it in 2 hours, right? But if he wants to do it, that means it's 120 miles. So if he wants to do it in 1 hour, he'll have to go 120 miles per hour. Not at all recommended. Let's go ahead and find it without having to find K first. That's possible too. So remember, we're going to set it up like this. Rate and time are inversely proportional. So rate 1 is to rate 2 as time 2 is to time 1. So we're going to get 60 over R equals time 2, which is 1, over 2. Now cross multiply, you get R equals 120 miles per hour. You can imagine that I like this method. So this is when t equals 1. Now, but I also see the extreme value of this method, so I want you to be masters of both methods, basically. That's why I'm doing both methods on every problem. We're almost done. Just a couple of more quick examples. First of all, joint variation. That's basically a slight variation of on direct variation. So let me explain what I mean. So we say that z varies jointly as x and y if and only if z equals k times the product of x and y. So here we have 3 items involved, right? And z is varying jointly as both of those values, right? So to say that z varies jointly as x and y is exactly the same as saying that z varies directly as the product of x and y. So that's just another way of saying it. We call this k the joint variation constant, or the constant of joint proportionality. All right, so suppose that we have a joint variation and that these two ordered triples satisfy it. So that means z1 equals kx1 y1 and z2 equals kx2 y2, right? If we divide those, we end up with z1 over z2 equals kx1 y1 over kx2 y2. K's cancel out, so we end up with z1 over z2 equals x1 y1 over x2 y2. Notice the order here, they correspond. 1, 2, 1, 2, 1, 2. We're going to remember that, because remember, joint variation is a kind of direct variation. So here we have u varies jointly as v and the square of w. So we're going to set it up as u equals k. So remember, as what? As v and the square of w. So w squared, like that. Let's set up our table. This time we're going to have u, v, and w represented in the table. So notice that u is 50 when v is 2 and w is 4. We want to find u, so u is going to be the unknown when v is 6 and w is 3. So first we're going to do it using the constant of variation, or variation constant. So we're going to use this row where all the values are known to find k. Now this is a relatively complex equation, so it's easier if we solve for k first. So notice we get k equals u over vw squared. Now we're just going to substitute. So plug in 50 for u, two for v, 4 for w. So 2 times 4 squared, like that. So we get 50 over, that's 2 times 16, so let's write it. Notice that 2 goes into itself once, into 50, 25 times. So we end up with k equals 25 over 16. So our variation equation for this scenario is u equals 25 over 16 v w squared. So we want to know u when v is 6 and w is 3. So we get u equals 25 over 16, v is 6, W is 3, so times 3 squared. So we get U equals, notice that 2 goes into 16, 8 times into 6, 3 times. So we have 25, so 75 times 9. $675 over 8. So remember, that will be U when V is 6 and W equals 3. All right, we can also do it without having to find K, but we have to carefully set up our proportion. So we get U1 over U2 equals V1 W1 squared over V2 W2 squared. Remember, the structure of the proportion comes from the equation. So you have U, V, and W squared. U, V, W squared. All right. So U1 is 50. U2 is U. V1 is 2. W1 is 4, so 4 squared, over V2, which is 6, times W2, which is 3, so 3 squared. So if we cross multiply, we get 2 times 4 squared U equals 6 times 3 squared times 50. We go ahead and divide both sides by 2 times 4 squared. We simplify. So we get U equals, now we know 2 goes into itself once, into 6 3 times. 4 squared is 16. Let me replace it with 16. And I know 2 goes into 16 8 times. It goes into 50 25 times. So we have 3 times 9 times 25. Which is 675 over 8. And of course, that's when V is 6 and W equals 3. Just as we got in the left example. All right. I promise this is the last type, combined variation. That's when one quantity varies directly as another quantity and simultaneously inversely as a third quantity. So it's not that bad. It's when you have both direct and inverse variation involved. So remember, combined variation occurs when one quantity Z varies directly as another variable, say X, and simultaneously varies inversely as another variable, Y. So look, if you only had Z varies directly as X, you would have had Z equals KX, right? And if you only had Z varies inversely as Y, you would have had Z equals K over Y. You would have covered the X, right? Now you have both, so what do you get? You get Z equals Kx, that takes care of the direct variation with X, and then over Y, which takes care of the inverse variation with Y. So now let's say we have two ordered triples that satisfy it. So we get Z, in other words, the ordered triples are X1, Y1, Z1, and X2, Y2, z2. So now we get z1 equals kx1 over y1, and z2 equals kx2 over y2. Now, if we look at the ratio of z1 and z2, we get z1 over z2 equals this expression, kx1 over y1 over z2, which is that expression, right? Then we do the outer product over the near product trick. So we get kx1 y2 over kx2 y1. So k's cancel out, so we get x1 y2 over x2 y1. So it's very nice proportion that we'll end up with at the end, which is this. So z1 over z2 equals x1 y2 over x2 y1. This is called the combined variation equation. This is called the combined variation proportion. Here's our last example, which is a great example of combined variation. I'm sure you've heard of the BMI, the body mass index. It actually varies directly as your weight and inversely as the square of your height. But for it to work, your weight needs to be given in pounds and your height needs to be given in inches. I guess it was developed in the United States. If a 6-foot tall man weighing 199 pounds has a BMI of 27, find the BMI of his wife if she is 5 feet 4 and weighs 128 pounds. So to do it the classic way, we know that BMI, which we can just use B4, varies directly as your weight. So KW, and inversely as the square of your height, right? Like that. So let's make a table. Remember, 6-foot tall man, so the height is 6. Weighing 199, so that's the weight. Has a BMI of 27. So now his wife the only issue you have to deal with here, notice, height needs to be in inches. So you can't say 6, you have to say 6 times 12. So why don't we just multiply it out and just write 72. That's better. Remember, the height has to be in inches, the weight has to be in pounds. All right, so as soon as you adjust that, you should be good to go. Now for the wife, the 5 feet give her 60 inches and then add another 4, so the height is 64. The weight is 128. And of course, the BMI is what we're trying to find. So we go ahead and use the first row of the table, given that all the information is known, to find the constant of variation. So why don't we cross multiply and solve for k first? So we have kw equals bh squared. So k equals bh squared over w. Now we'll substitute these values in here. So b is 27, h is 72, so we need to square it, and then over W, which is 199. So let's go ahead and calculate that. So we have 27 times 72 squared, and then we're going to divide that by 199, and we get approximately 703. Yeah, let's go with 703. Now we can write the equation as B equals 703 W over H squared. So let's see if we can find the BMI for his wife. So we're going to have to plug in 703, and then W, the wife's weight was 128, and we need to divide that by the height squared, so 64 squared. So if we really want to be accurate, we should take maybe a few more of these digits. So let's take at least two places. So 703.36, just for better accuracy. So let's go with 703.36 times weight, which was 128. Let's try that. So we have 703.36 times 128 divided by, actually I wanted to exit that first and then divide it by, doesn't make any difference, it just looks nicer. 64 squared. All right, so that we can round. So the wife has a BMI of approximately 22. Okay, so now let's go ahead and try to figure it out without finding the variation constant first, using the variation proportion. So remember, we need to set that up correctly, and we're going to use the equation, the general variation equation, to set up the proportion. So we know that B and W vary directly. So if you have B1 over B2, you know you'll have W1 and W2 in the same direction because of the direct variation. But H has an inverse relationship with B, so instead of having H1 squared over H2 squared, we're going to have H2 squared over H1 squared. Okay, so now we substitute. So we have B1 over B2, so that's 27 over, we don't know what B2 is, we'll just call it B. That's the wife's BMI. So we're going to get H2. That comes from here, H2, so 64 squared, H2 squared, times W1, that's 199, over H1 squared, so 72 squared, times W2, which is 128. Now if we cross multiply, we get 64 squared times 199b equals 27 times 72 squared times 128. So B is going to be all that on the right, 27 times 72 squared times 128 divided by 64 squared times 199. So let's go ahead and get some help from our calculator. So we have 27 times 72 squared times 128 and then we're going to divide that by 64 squared times 199. Then we're going to hold our breath. Hope we didn't make some kind of a careless error. All right, so notice it's extremely close to what this result was, the previous result we had, which was 21.98 if you recall. But if you're going to go really accurate and pick one of these two, pick this one, because notice with this one we didn't do any rounding. With this one we had a little bit of rounding right there. That's 703.36, of course. So we did do a little bit of rounding there, but with this one we didn't do any rounding. So this would have been more accurate than this one. But both of them, if you're going to round to a nearest whole number, are basically going to be around 22. So the wife's BMI is 22. All right, so there is variation for you in all its various forms, and make sure that you practice these and stay safe until our next video.